Hi, this is John Whitaker for the Probability 1 graduate level class, and this is our 8th video lecture. And last time we had some facts about a uniformly distributed random variable, and I want to conclude with one more characteristic for a uniformly distributed random variable. Let's recall for a uniformly distributed random variable, the probability density function, let's give this variable a name, x. The probability density function of x is, and so it was f of x equals to, it was 1 over b minus a if x was an element from a to b, and it was 0 otherwise. And from that definition, and the definition of a CDF, so this we call, this is 1, 2, the CDF, cumulative distribution function, of a random variable x is big F of x, which is equal to, it is the probability that big X is less than or equal to little x, which is equal to, that's what we'll write. And we're going to now look at the CDF for a uniformly distributed random variable. Okay. So here, let's let x be a uniformly distributed random variable. Then the CDF of x is, and so instead of saying what it is, what I'm going to do is compute it here. So first of all, let's note, let's call it f of t. Okay? And so here, what is f of t going to be equal to? Well, first of all, let's talk about t values. If t is less than a, then f of t, which equals to the probability that big X is less than or equal to t, will be equal to the integral from minus infinity to t of f of x dx. But since t is less than a, the f of x is going to be equal to 0 here. So it's the integral from minus infinity to t of 0 dx, which is just equal to 0. But what if t is in between a and b? That's what we'll consider next. Then, big F of t, which would equal the probability that x is less than or equal to t, well, it would be the integral from minus infinity to t of f of x dx. Remember, f of x is non-zero only when x is between a and b, so this will be the integral from a to t in this case, of f of x dx, which would be equal to the integral, well, here the f of x is 1 over b minus a. And so this is going to be 1 over b minus a evaluated, well, times x, excuse me, evaluated when x runs from a to t. So this ends up being t minus a over b minus a. Now, finally, if b is less than or equal to t, then f of t is going to be equal to the probability that x is less than or equal to t, which is equal to the integral from minus infinity to t of f of x dx, which would be, in this case, the integral from a to b of f of x dx, which is 1. Okay? So over here on the side, we'll write a summary of what the CDF for uniformly distributed random variable is. So the CDF for a uniformly distributed random variable is, I'll call it big F of t, and it's a piecewise defined function. It's 0 if t is less than a. It was t minus a over b minus a if a was less than or equal to t, which was less than b, and it was defined to be 1 if t was bigger than b, bigger than or equal to b. That's what we have. So that's a little bit of another characteristic for a uniformly distributed random variable. It's also a little bit more experience with us about the CDF, calculating CDF. Well, the next continuous random variable that I like to look at is one that's called an exponential. So the definition for an exponential random variable is the following. It says, definition, a continuous random variable x is said to be an exponential random variable if its PDF is f of x equaling, it's a piecewise defined function, it's e to the minus lambda, e to the minus lambda x times lambda if lambda is greater than, if x is greater than or equal to 0, and it's equal to 0 otherwise, where lambda is some fixed number that's bigger than 0. In this case, we say x is exponentially distributed, with parameter lambda. Okay. You know, there's always the fact that we want to have be the case. That is, if we integrate from minus infinity to infinity, the PDF, that's lambda e to the minus, well, let me just write down as f of x at this point, dx, which equals to, here, the f of x for an exponentially distributed random variable is 0 a lot of times. The times where it isn't 0 is from 0 to infinity. And in that case, it's lambda e to the minus lambda x dx. This is e to the something. To integrate e to the something, you need to have its derivative to do use substitution. The derivative of the something. The derivative of minus lambda x with respect to x is minus lambda, which we almost have. So I'll write down it's minus the integral from 0 to infinity of e to the minus lambda x minus lambda dx. So I've inserted a minus here and a minus here. And then through use substitution, what you get is this is e to the minus lambda x evaluated from 0 to infinity. Now, this is supposed to be an improper interval. I should have maybe limits as a dummy variable, like t goes to infinity, and substitute in for infinity t. But here I'm just going to say, look, when you have huge numbers for x, remember lambda is positive, so when you put minus in front it becomes negative. These becomes huge negative numbers as the powers. Even huge negative numbers are 0. I've forgotten the minus here. Let's put that in front. So here I get minus 0, and then using the fundamental theorem of calculus, it would be minus what I get. So minus, a minus, that minus. When we stick in 0 for x, the power becomes 0. And so this ends up just being 1, because e to the 0 is 1, and minus a minus makes a plus. So that's what we get, and that's what we were hoping to get. Well, we'd like to look at the expected value of an exponential distributed random variable, and that's what we'll do next. And a note, or here's a fact, if x is exponentially distributed with parameter lambda, then the expected value of x is equal to 1 over lambda. Let's look at the proof. Now, the expected value of x, in this case, is going to be equal to the integral from minus infinity to infinity of x, f of x dx. F of x is the PDF for an exponentially distributed random variable. A lot of times it's 0, so this, where it's non-zero, from 0 to infinity. X lambda e to the minus lambda x dx. Okay, that's what we have. We're trying to integrate. And here to integrate this, what we do is integration by parts. So we let u be equal to x, du will be equal to dx, dv will be equal to lambda e to the minus lambda x, that's the guy we can integrate to get v, and that would be minus e to the minus lambda x. Here this should have dx with it. And so, here's what we get using integration by parts. So the expected value of x, which is integral from 0 to infinity of x lambda e to the minus lambda x dx is uv. So that's going to be minus x e to the minus lambda x, evaluate from 0 to infinity, minus the integral d du. So that's going to be minus from 0 to infinity e to the minus lambda x, and then du was dx. I'm going to be a little bit more careful here. I'll say that the limit as t goes to infinity of minus x e to the minus lambda x 0 to t. Here, this is going to be minus, and look, we have e to the something. The derivative of the something is minus lambda. I got the minus, I don't have the lambda, but I can stick in a lambda because it's a constant. And so I'll write down e to the minus lambda x minus lambda dx. And I've inserted this lambda, and I have to compensate by putting a 1 over lambda outside the integral. Okay, here we stick in using the fundamental theorem of calculus t. We get the limit as t goes to infinity of minus t e to the minus lambda t. Then when we stick in 0, we're just going to get 0. And here, this is minus 1 over lambda times, so this will be e to the minus lambda x, which we have to evaluate from 0 to infinity. This is equal to, well, this is minus infinity times 0, and so that's an indeterminate form, and we can put it in L'Hopital's rule form by saying this is minus t over e to the lambda t. Minus 0 is nothing, it's minus 1 over lambda. Here, I'm going to go ahead and imagine sticking in x values, I should say, getting really, really big, going towards infinity. This will go to 0. Okay? And then when I stick in 1, I'm going to have when I stick in 0 for x, I'm going to have minus 1. Okay, that limit as t goes to infinity of minus t over e to the lambda t is minus infinity over infinity. And so we use L'Hopital's rule, which becomes the limit as t goes to infinity. Taking the derivative top, I get minus 1 over the derivative bottom, which was lambda e to the lambda t. And then here we have minus, well, really, it's a minus 1 over lambda times a minus 1 that makes it plus 1 over lambda. Okay, now as t goes to infinity, since lambda is positive, this goes to infinity. This is positive. The bottom is going towards infinity. Minus 1 divided by something getting really, really big goes to 0. So this is equal to 0 plus 1 over lambda, which equals to 1 over lambda, which is what we predicted. Next thing we want to know is about what is the variance. So as a fact, if x is exponentially distributed, with parameter lambda, then the variance of x is going to be equal to 1 over lambda squared. Okay, to prove this, let's remember we had a formula for the variance of x, and that was the variance of x is equal to the expected value of x squared minus the expected value of x to b squared. We have already got the expected value of x as 1 over lambda. But we need to know what the expected value of x squared is. So let's work on that. It's equal to the integral from minus infinity to infinity of x squared f of x, which is PDF of x dx. Remember, this is 0 when x is less than 0, so this ends up being an integral from 0 to infinity of x squared times lambda e to the minus lambda x dx. Okay, we're going to have to use integration by parts again twice in this case. So here we're going to let u equal to x squared. That means du is equal to 2x dx. dv will be equal to lambda times e to the minus lambda x dx. And integrating that, we're going to get v is equal to minus e to the minus lambda x. So the expected value of x squared now is equal to, well, it was uv, so it's minus x squared e to the minus lambda x minus integral, and oh, don't forget this is to be evaluated from 0 to infinity. Minus integral, and what integral is this? This is v du, so it's minus e 0 to infinity, minus e lambda x, and then it would be 2x dx. So I'm going to rewrite this as the limit, again, inserting the variable t. T goes to infinity of minus x squared over, I'm going to write this down, as e to the lambda x, evaluated from 0 to t, minus, here I'm going to have to use, well, I'm going to pull out a 2. And then this is going to be minus e lambda x, don't forget it's an integral from 0 to infinity, x dx, and we'll have to use integration by parts again. Here, we get a limit as t goes to infinity of minus t squared over e to the lambda t minus what I get when I stick in 0, which is 0. Here we're going to let u be equal to x, du will be equal to dx, dv is equal to e to the minus, well, it's got a minus sign in front of it, minus e to the minus lambda x. To integrate that, we need a minus lambda here, so imagine putting it there, and then we have to divide by 1 over lambda. That is dx, and that's what dv would be. And so here we get minus 2 times, it would be uv, so that would be 1 over lambda x e to the minus lambda x, evaluated from 0 to infinity. And then minus what we get when we have it's v du, so 1 over lambda e to the minus lambda x, du is dx, and that's where we are. Here, you're going to use L'Hopital's rule twice. This is minus infinity over infinity. What it's going to boil down to, you do it twice, it becomes minus 2t over lambda e to the lambda t. You do it again, you're just going to get 2 over lambda squared e to the lambda t. And the bottom is going to go to infinity, so the top was minus 2, so you're going to end up getting 0. And so here we have minus 2 times. Here we're going to put the e to the minus lambda x in the bottom. We're going to have an indeterminate form of infinity over infinity. It's going to go to 0. When I let x be 0, we're going to get 0. So this first part is going to be 0. Minus, so this interval right here, we got to put from 0 to infinity. That's what we're working on. You can pull out the 1 over lambda, and what we need is e to the minus lambda x is what we have. We need a minus lambda. Let's put that in, dx. And to compensate for that minus lambda, we're going to put a minus 1 over lambda here, out front from 0 to infinity. Okay. Now, that's going to be equal to, so we have minus 2 times, there's two minuses there, so that becomes a plus. And here it's going to be, so it's plus 1 over lambda squared, and then it would be e to the minus lambda x evaluated from 0 to infinity. So that's equal to minus 2. When you stick in huge numbers for x, as x goes to 50, this part goes to 0. So it's going to be 0 minus 1 over lambda squared. When you let x be 0, you just get 1. And this is equal to 2 over lambda squared. That's what we get for the expected value of x squared. Okay. Okay. So, the variance of x, which is equal to the expected value of x squared minus the expected value of x to b squared. This is going to be equal to 2 over lambda squared minus it's 1 over lambda to b squared, which is 1 over lambda squared. So we end up getting 2 minus 1, which is just 1, over lambda squared, and that's what we said the answer was going to be. That is that proof. That's pretty much all I wanted to say about an exponentially distributed random variable. And what I wanted to turn to next was a different continuous random variable called a gamma random variable. So here's what it says. A gamma random variable is a continuous random variable x whose PDF is it's f of x, which is equal to the following. It's equal to lambda times e to the minus lambda x, all that times lambda x to the alpha minus 1 over some function called the gamma function of alpha, and that's if x is greater than or equal to 0, and it's 0 otherwise. And that's what it's defined for some lambda greater than 0 and alpha greater than 0, where I need to find what that gamma function is. Where gamma of alpha is defined to be an interval from 0 to infinity of e to the minus x, x to the alpha minus 1 dx. Okay. In this case, x is said to be gamma distributed with parameters lambda and alpha. Before we do anything about a gamma distributed random variable in terms of its characteristics, I want to talk a little bit about the gamma function. And so here's a fact. I'm going to ask you to prove this in the next homework assignment. but as a fact, if n is an element of the natural numbers, then gamma of n is equal to n minus 1 factorial. That's what it's equal to. So we'll ask you to prove that. I'll ask you to prove that for the next homework assignment. But I'm going to prove something about gamma of n next, or gamma of alpha next. Okay, so in particular, as a fact, gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. Let's prove this. Okay. So note, gamma of alpha by definition is equal to the integral from 0 to infinity of e to the minus x, x to the alpha minus 1 dx. Now, if we use integration by parts, we let u be equal to e to the minus x, and du will be equal to minus e to the minus x. I'm sorry. Let's back up. Let's let u be equal to x to the alpha minus 1. I made a mistake. Then the derivative of that will be alpha minus 1 times x to the alpha minus 2. And if we let dv be equal to e to the minus x dx, then v is going to be equal to minus e to the minus x. That's what the antiderivative of dv is. Okay. And so, what we get is gamma of alpha is equal to, well, it's u times v, so that would be minus e to the minus x, x to the alpha minus 1, evaluated from 0 to infinity, minus the integral of v, which is minus e to the minus x, from 0 to infinity, du, which is alpha minus 1, times x to the alpha minus 2 dx. Okay. When you stick in the bottom, the 0, you're going to get 0. When you stick in infinity, it's going to be an indeterminate limit form, depending upon what alpha is. But eventually, taking L'Hopital's rule, if needed, a bunch of times, where you stick the e to the minus x in the bottom as e to the x, you're going to end up being 0. This whole thing goes to 0. So this is going to be equal to 0 minus, so the minus here and the minus here will make a plus. 0 to infinity, this is e to the minus x, and I can pull out, let's pull out the alpha minus 1. And then this is x to the alpha minus 2 dx. This is equal to alpha minus 1. Now this integral is nothing more than gamma evaluated at alpha minus 1. And that proves the theorem. And that the gamma of alpha minus 1 is the integral from 0 to infinity to e minus x, x to the alpha minus 1 dx. Okay, so that proves that fact. Next thing I want to do is show that if you integrate the PDF of a gamma random variable, you get 1. So here, let's just note that the integral from minus infinity to infinity of f of x dx equals, well, this will become the integral from 0 to infinity. Here it would be, I think it was lambda e to the minus lambda x to the, it was to the alpha minus 1 over, this is all integrating, gamma of alpha. Let me make the integral a little bigger. Okay, that's what we have, dx. Okay. All right, what we're going to do is we're going to do a u substitution after pulling out the 1 over gamma of alpha here. The integral from 0 to infinity, lambda e to the minus lambda x to the alpha minus 1 dx. And the u substitution we're going to do is we're going to let u be equal to lambda to the x. Then du will be equal to lambda dx. So this lambda and that dx makes du. So we end up getting 1 over gamma of alpha. And look, when x is 0, u is going to be 0. When x tends towards infinity, since lambda is positive, u is going to trend towards infinity. So these limits of integration stay the same. And here this is going to be e to the u. Here is u to the alpha minus 1. Okay? And lambda dx makes du. Well, this is nothing more than gamma of alpha, even though it's written in terms of the dummy variable u. And so that's equal to 1. Okay? 1 over gamma of alpha times gamma of alpha is equal to 1. And that's what we expected. Okay, next we're going to do the expected value. Gamma. Is fact. If x is a gamma random variable, with parameters lambda and alpha, then the expected value of x is equal to alpha over lambda. Let's prove that. So the expected value of x is the integral from minus infinity to infinity of f of x dx, which is going to be equal to, because f of x is defined to be 0, except from 0 to infinity. So it's x, and here f of x was lambda e to the minus lambda x, I think. And then it was lambda x to the alpha minus 1 over gamma of alpha dx. So that's what we have. And so what we're going to do is we're going to take this x and this lambda, put them together and say, well, that's the integral from 0 to infinity of e to the minus lambda x. That's that part. And this lambda and x will combine here to give us lambda x to the alpha over gamma of alpha dx, which we will put a 1 over lambda, integral from 0 to infinity, of e to the minus lambda, so I'm going to put a lambda here, lambda e to the minus lambda x to the alpha over gamma of alpha. So all I did in that last move was I stuck in a lambda and compensated for that multiplication by lambda by having out in front 1 over lambda. So that 1 over lambda times lambda is just 1. And I can do that because lambda is a constant with respect to x. Okay. And we pull out the gamma of alpha underneath as well. So we have 1 over lambda gamma of alpha. And then this is the integral from 0 to infinity of lambda e to the minus lambda x to the alpha dx. And just like what we did before with the u substitution, we'll let u be equal to lambda x, and du will be equal to lambda dx. So our integral becomes 1 over lambda gamma of alpha. Here, this is the integral from 0 to infinity, e to the minus u. Here is u to the alpha. The lambda and the dx makes du. And so you can see this is a function of some evaluation of the gamma function. It's really gamma of alpha plus 1, it looks like. Okay, because this should be alpha plus 1 minus 1 to get alpha. But the gamma of alpha plus 1 by the previous fact, I think it's alpha times gamma of alpha by the previous fact. This gamma of alpha and this gamma of alpha will cancel, and we're left with alpha over lambda. And that's what we predicted, or said it would be. So that ends that proof. Next thing we'll do is the variance. Okay. Here's a fact about it. If x is a gamma random variable, with parameters lambda and alpha, then the variance of x is equal to alpha over lambda squared. Okay, let's start working on the proof. And so let's recall the variance for continuous random variable, for any random variable, expected value of x squared minus expected value of x to b squared. So we need to figure out the expected value of x squared. Okay. That's going to be integral from 0 to infinity, because of the way that f of x is defined, of x squared times equals lambda e to the minus lambda x to the alpha minus 1 all over gamma of alpha. We're going to do similar tricks to what we did to the expected value for x. Similar tricks to what was in that proof. Okay, that is, we can pull out, well, first of all, we can take a lambda and an x that we had inside the integral and combine it with the lambda x to the alpha minus 1 to make alpha. I still have an x, this is from 0 to infinity, still got e to the minus lambda x, and it's still over gamma of alpha dx. Okay, we could put in a lambda. Now I'll pull out the gamma of alpha. So I'm putting in an extra lambda. So now I'm going to have 0 to infinity, lambda x, e to the minus lambda x to the alpha. I pulled out the gamma of alpha, so dx. And now this lambda x here can combine with the lambda x to the alphas. And I have 1 over lambda, gamma, well, gamma of alpha is in the bottom. 0 to infinity, this would be e to the minus lambda x to the alpha plus 1 dx. Now, let's put in another lambda. So this would be 1 over lambda squared, so another lambda in the bottom to compensate for the lambda that I'm going to stick inside the integral. Okay. And then we're going to make a u substitution, which I'll do right here. So u is going to be equal to lambda is x, as we have been doing, and then du is going to be equal to lambda dx. We'll make that substitution. Here's what we come up with. Okay, so we're going to get equal to 1 over lambda squared gamma of alpha. This is going to be the integral from 0 to infinity. This is going to be e to the u. This is going to be u to the alpha plus 1 du, sorry. And so this integral, constant in front stays the same. But this integral is gamma of alpha plus 2. Well, that's equal to 1 over lambda squared, gamma of alpha. This will be alpha plus 1, gamma of alpha plus 1, which will be equal to 1 over lambda squared, gamma of alpha, still using that previous fact that we computed. This will be alpha plus 1. Now, gamma of alpha plus 1 is alpha times gamma of alpha. And then the gamma of alphas are going to cancel, and so we're left with alpha squared plus alpha over lambda squared for the expected value of x squared. That's what we just had. So the variance of x, which equals to the expected value of x squared minus the expected value of x to b squared, is equal to, here this was alpha squared plus alpha over lambda squared. Remember, this is alpha over lambda, so it's minus alpha squared over lambda squared. And so we get alpha over lambda squared, and that's what we predicted. So that's the proof of the variance, of what the variance is for a gamma random variable. I want to conclude today by looking at, or initially describing, the most famous of continuous random variables. So we'll just introduce it. So as a definition, a continuous random variable x is said to be normally distributed if its PDF is, well, its alpha of x is equal to 1 over the square root of 2 pi, and the bottom is a number sigma, it's going to be positive, e to the minus quantity x minus mu to b squared all over 2 sigma squared. Okay. In this case, x is normally distributed with parameters. Our book is going to say mu and sigma squared. And ladies and gentlemen, that's enough for this lecture. Thank you very much.